I welcome you all to the next session on enumeration of unlabeled graphs. In the previous session, we have seen about enumeration of labeled graphs. Now we are going to see about enumeration of unlabeled graphs. Here more specifically, we are going to see about unlabeled rooted trees and unlabeled trees. First, we are going to find rooted trees, and using the concept of rooted trees, we are going to find the enumeration of trees. What is a rooted tree? It's similar to a tree. It is just a tree. Let me draw a simple rooted tree. Yes, it's a tree. But here, one vertex is considered to be a peculiar vertex called as root. Generally, the roots are denoted by R. This is an example for a rooted tree. This is another rooted tree. So, we are going to find how many rooted trees are possible for a given n vertices. For that, we are going to make use of two concepts. One is generating function, another one partitions. By combining these two concepts, we are going to generate enumeration. Before moving on to the unlabeled rooted trees, counting of unlabeled rooted trees, let us see the basic definitions of generating function and partitions. Okay. Let me start with generating function. It is nothing but a power series. A0 plus a1x plus a2x square plus etc. Here x is a dummy variable. What's the meaning of dummy variable? It has no importance. The value of x doesn't have any importance here. Suppose I have generated such a function for a graph, for example, rooted unlabeled tree. What does this coefficients a0, a1, a2, etc. mean to your graph? Here, this a0 represents the counting of unlabeled rooted tree with 0 edges. This a1 gives me number of unlabeled rooted tree with edge 1. Since the power of x is 1, I am mentioning number of edges as 1. Similarly, what is a2? a2 gives me the counting of number of labeled trees with n vertices with edges 2. So, the coefficients are of importance here, but not x. That's the meaning. So, we are going to generate a function like this using partitions, and looking at the coefficient itself, we can say this graph with a particular criteria will be of this number. Number of such graphs will exist. So the coefficient is important. So what is coefficient of x power k? A power k, which is the required number. In the very earlier classes, we have learnt about binomial expansion, a very simple binomial expansion, 1 plus x whole power n. For a positive integer, the expansion is nc0 plus nc1 into x plus nc2 into x square plus etc. ncnx to the power n. What is this coefficient here? Coefficient of x power k is nck. Otherwise, this can be written as nck. What is combination? Combination is nothing but selection. Selecting what? K objects out of n objects. So, selecting of k different objects from n objects is said to be nck. So, I have given an example for a power series, and I have mentioned about the coefficient. The coefficient here is nck. Here it represents number of selection. Now this is valid only if we select different items out of n objects. And this one doesn't holds for repetition of objects. Suppose for example, I am having n objects. I can select the objects that are taken already. I can repeat the objects. I can allow unlimited repetitions. Suppose I want to select numbers from 1 to n and I am going to select k such numbers. For example, suppose I am choosing 1. Second time I want to choose 2. Next also I want to choose 2. Next also I want to choose. So the repetition is allowed here. The thing is you have to arrange the numbers in increasing order. So if I arrange the numbers, the selections in this way, here the repetitions are permitted. So I have selected k objects, but even though the element selected will be 1, 2, some 7, etc. But 2 is repeated thrice. So in this case, I cannot apply this NCK. So what I have to do? What I am going to do is I am going to convert these numbers into different numbers. Actually 2, 2, 2 are repeated numbers. They are same. They are not different. But what I am going to do is I am going to convert this sequence to a sequence of numbers which are all different. When they are different, I can move on to this concept and I can make use of this formula. So what I am going to do is I am going to convert the repeated numbers as a distinct numbers, otherwise called as different numbers. What's the procedure I am going to apply in order to convert these repeated numbers? I am going to add 0 with the first element, 1 with the second element. You just imagine or just make the count. I am going to add 0 with this, so the number become 1. I am going to add 1, so it becomes 3. I am going to add 2, so this becomes 4. Here 3, the number becomes 5. Look at the sequence now. 1, 3, 4, 5. So I have omitted, I have moved away from repetitions just by adding 0 to first element, 1 to second element and so on. That is finally we are going to select k elements. So finally I have to add k with the last element. Now what happens? Let me see with an example. Let me have 3 objects, 1, 2, 3. So n is 3, number of objects is 3. Now repetitions allowed is 3. You have to select 3 objects out of n objects with repetitions. I am going to select 3 objects out of 3 objects with repetitions. This may be 1, 2, 2 or 1, 1, 2. But for your understanding, let me take, if I have chosen all the 3 elements are same. It may be 1, 1, 1, 2, 2, 2, 3, 3, 3. So I have selected 3 elements from this objects 1, 2, 3. But there is a repetition. How I am going to convert these repeated objects into distinct objects? I am going to apply the concept. Add 0 to first element. Add 1 to first element. Add 2 to third element. Here also the same procedure. Add 0 to first element. Add 1 to first element. Add 2 to third element. The same procedure followed. So look at this. If any of the form is chosen with repetition here, either this or this or this, all the sequence now obtained will be a sequence with different elements. But look at the criteria here. I have been provided with only 3 objects, 1, 2, 3. But finally I am getting, in this case I am getting 4, 5 extra numbers which are not in the list. Here the 4 which is not on the list. So I have to extend my objects, available objects. So I have to extend up to what? Up to 5. How I can find that? N plus k minus 1. What is n plus k minus 1? 3 plus n is 3. I am going to select 3 objects, that is 3 minus 1. 3 plus 3 minus 1, 6 minus 1 is 5. So, I have to extend the objects to 5. Now, this becomes the problem now have been converted to, along with the 5 elements, along with these 5 elements, I am going to select 3 different elements. Originally, I have given with only 3 objects. And I am going to select 3 objects out of this, but repetition is allowed here. But the repetition is going to converted as a distinct objects by just by adding 0, 1, 2, etc. Now, out of this addition, this sequence becomes a sequence of elements without repetitions. But the elements, the original n objects has been extended to n plus k minus 1. So, selecting 3 objects from 3 objects with repetition is same as selection of 3 objects from 1 to 5 elements. That is n plus k minus 1 elements without repetitions. So, I have converted my problem to without repetition. So, I can make use of this formula NCK. What is NCK? Selection of k objects out of n objects. So, here my extended objects is n plus k minus 1. Out of this n plus k minus 1, I am going to select k objects. So, my coefficient AK becomes n plus k minus 1 CK. So, these are the 2 formulas used in creating unlabeled rooted trees. That one's without repetition, here with repetitions. But we are going to see the concept with repetition, because in a graph I may have repetitions. I cannot restrict that it can have only distinct collections. If I restrict so, I won't get different types of graphs. But my aim is to collect all possible rooted trees with the given n vertices. So, I need repetition. So, the main thing is I am going to make use of this formula. Total number of objects n plus k minus 1 with the k repetitions. With the k elements, okay. Another example is given here. Now, I am having 3 elements. I am going to select 2 elements. So, 1, 2, 3, I am going to select 2 elements. Here repetition is allowed. So, I am going to select only the repetition part. 1, 1, 2, 2, 3, 3. 1 plus 0, 1 plus 1. 2 plus 0, 2 plus 1. 3 plus 0, 3 plus 1. This yields me 1, 2. This yields me 2, 3. This one 3, 4. So, my set, original set is extended up to 4. That is using n plus k minus 1. N is 3, k is 2 minus 1, which is 4. So, number of elements has been increased. So, now the selection can be written as n plus k minus 1 ck. That's what about generating functions, and I have to club this concept with the graphs. That will be explained later. Now let us see about partitions. Okay. Take a positive integer. Let us discuss about partitions in positive integers. For example, 5. 5 can be partitioned as 5. Simply I can write it as 5 or 4 plus 1. 3 plus 2. So, splitting of element 5. So, a number p, positive integer, can be split as lambda 1 plus lambda 2 plus etc. lambda q. The criteria is it should be arranged in descending order. The greater value should precede. And all the lambdas should be greater than or equal to 1. It should not be 0 or negative. Once again, we see the example. 5 is 5. 5 can be written as 4 plus 1. Look at the order. I have written in decreasing order. 5 is 3 plus 2. 5 is 3 plus 1 plus 1. These partitions can also be written in the format of 5 within brackets, 4, 1 within brackets, 3, 2. 5 is partitioned as 3, 2. 5 is partitioned as 3, 1, 1. 5 can also be partitioned as 2, 2, 1, 2, 1, 1, 1, 1, 1, 1, 1, 1, 5 times. Whenever there is a repetition, this can also be written as 2 square, 1, 2, 1 cube, 1 to the power 5. The power value represents repetitions. And these lambda values are called as parts of partition number P. Parts. 2 is a part, 2 is a part, 1 is a part. These values are called as parts of repetition. Sometimes these partitions can also be done either with restriction or with unrestricted. These are all unrestricted. You can write it in any way. Suppose some restriction is imposed. What happens? Let us see two types of repetitions. Let me give you an example. No repetition of any part. Any part should not be repeated. Take this example 2, 2, 1. Here 2 and 2 are repeated. But I am restricting that no part should not be repeated. So lambda I should not be equal to lambda j for all I comma j. So I should not select such partition. I have to select a partition without repetition. Means I can go with first, second partition, third partition. In all other cases, repetitions are there. Next example, no part greater than k. Suppose let me take k to be 5. In a 3. In a partition of 5, no part greater than 3. I have to select a partition which consists of only part which are less than or equal to 3. Less than or equal to 3 or no part greater than 3. Both are same. So less than or equal to 3 includes this one, third example, fourth one, fifth one, sixth one, seventh one. The first two will not be included. That is number only less than or equal to 3. So 4 and 5 should be excluded in the partitions. Total number of partition of given integer. So how many partitions are here? 1, 2, 3, 4, 5, 6, 7. So 5 contains 7 partitions. I have written all the partitions of 5. So total partition 7. Here total number of partition of given integer b can be obtained with the help of generating function. So slowly they have clubbed the concept partition with generating function. So in order to find the number of partitions, I can obtain that number of partitions can be obtained using generating function. So for your example, number of partitions without repetitions of an integer. So I have to collect the partition of an element p. There the repetition is not permitted, and number of partitions without repetition of an integer k less than or equal to p gives me coefficient of x bar k in 1 plus x into 1 plus x square plus etc. 1 plus x to the power p. So when I multiply all these things and if I collect the coefficient of x power k, coefficient not x, coefficient of x power k, that gives me number of partitions without repetition of an integer k which is less than or equal to p. So I am going to count the number of partition of k without repetition. That k should be less than or equal to p. That's all about partitions and generating functions. Now in the next video we will see how these two concepts, how they are incorporated in finding enumeration of a rooted unlabeled trees. Thank you.